Well, good afternoon, evening, everybody. Thanks for the invitation. Um, we'll take a walk through a little optics and microscopy and some crystal gazing. As Shirley mentioned, I was a particle hunter, and that turned into more of a stability seeker as well. So we used all sorts of microscopy in the industry to first look at contamination, and then to look at products on stability, and to look at products as the customer received them. So sometimes that wasn't very welcome because we'd find things, but hey, we're there to make sterile and stable products to benefit everybody. So it all works out in the end. Well, I'm going to start off the presentation with a few images, and I think you can see my cursor on the screen, right? So, stardust, I don't ever get to look at too much of that, but in the macro world, we may look at a number of wonderful objects and look at biological chemical structures. But it's a pretty cool world to inhabit, the microscopical world. Just a desk image of pollen grains and another one here of a bacteria. So there's just a multitude of things we can see microscopically. And I'll talk about optical microscopy, light microscopy, but we can't ignore electron and microscopy and other spectroscopies that go along with it that help us to characterize materials. But the whole purpose of reviewing this for you all is to show you some crystallography and some images. So my general outline is looking at light and color, the optics of microscopes, the nature of material, how we analyze material, and hey, is it art or analysis? So light and color matter quite a bit to we humans, to how we perceive everything, both the level of light and the kind of color that we're perceiving. And industrially, the way we observe items is pretty critical. When you're in the supermarket, the color temperature of the illumination and the illumination balance is pretty key in marketing and presentation. And there's certain units of measure that we use to verify that we're sitting in a place that we need to be. But it's pretty loosely controlled in the general setting. It's pretty tightly controlled in various industries, especially pharmaceuticals. And for presentation's sake, the packages have to be designed well enough to hold the item. They have to be stable, and they have to pass muster when it comes to inspection. And so both the light intensity, the brightness, and the illuminance need to be measured as you're processing and releasing materials. We humans perceive in a rather narrow band of the electromagnetic spectrum, and you'll recognize the rainbow colors here in this band, and also the more quantitative information about where they reside. It's always surprising to me to think that we creatures developed in this narrow band of seeing when all this other stuff exists. And of course, we can take photomicrographs and regular photographs with energy somewhat outside of the visible spectrum, but we pretty much reside within these boundaries. So along with that concept of illumination and color, we've also got the properties of that light beam as it's passing through material. And refraction is the proportion of the speed of light through the medium compared to the speed of light through a vacuum. So in other words, the refractive index of a material is always going to be above 1. The refractive index of water is 1.33. Of air, it's 1.0 with a lot of zeros and then some digits. For common things like oils, maybe 1.4, 1.5. Minerals will get up into 1.6 or so. And really highly refractive materials like zircon or diamond are very, very high. Even iron oxide rust is very high. So you can use that to your advantage. If you know the refractive index of a material, you can try to determine that refractive index in an unknown, and it might make sense to track down other properties to verify what it is. So when we have on the left here, when we have a light beam that's impinging upon a more solid material, it could be liquid, it could be a transparent solid. You'll have a bending of the light as it passes through this medium. And it can be described quantitatively, it can be measured. And it's used to our advantage, let's say in gemology, where we have certain cuts of the gem that produce high reflectivity and light entrapment by a physical principle called the critical angle. That is, when the light ray is passing between two substances, depending on the refractive index of the two substances, you may have the light passing through, being refracted, being reflected, being trapped. And so that could be used to your advantage. On the right-hand side, this diagram from an older textbook, it's showing you cut planes of focus in a microscope. So think, conceive of this cutaway looking at this grain trapped between a microscope slide and a cover slip. And so let's say we have a grain of sand here and we have a liquid or refractive index immersion oil that's surrounding the grain. And when we get really close to matching the refractive index of the solid and the liquid, now all of a sudden the different wavelengths of illumination start to behave differently. You start to see the differences and you start to split apart the component wavelengths of that white light into discrete colored elements. So what's so good or bad about that? Well, what's bad about it is it gives us a chromatic aberration, which affects everybody looking through lenses. But what's good about it is if you can control it, if you hold that specimen at a certain temperature and you can quantitate the color that you're seeing, it can tell you what that material is. It can tell you something about the relative refractive index. So just something as simple as that can be used diagnostically. So for microscopists and photographers, image quality matters. I mean, it's one of the elements of our craft. So for microscopy, using collimated light's pretty important. Making sure the illumination axis is coincident with the optical axis. We need aligned focal planes. That is, at every convergent focal plane within the microscope, it needs to be coherent. It needs to be sharp. We want to control the excess light, and you can do this in a variety of ways, and maybe all together, using neutral density filters, iris diaphragms, and controlling the lamp intensity. But when you control the lamp intensity, you want to make sure you're not affecting or controlling the color temperature, because that can give you a different perception of the color of the object. And then there's lens perfection. I mentioned the splitting of your component white light into different colors. That would be chromatic aberration. And in poor lenses, you start to see that at the fringes of the image, and you'll see it at the fringes of the field. And good optics manufacturers go to great lengths to correct their lenses to overcome both of these aberrations, spherical and chromatic. And it's sort of a go, no-go process, I believe. They do their best to make them, and then when they quality control their lenses, it's pass, fail, pass, fail. Finally, the spherical aberration is just having different focal points for component illumination, and it gives you a fuzzy image if it's not aligned crisply. So how do we go about identifying things? For us, it's a stepwise process. We come from the outside and go to the inside. We start low and go high. A lot of folks we find in the industry, I found this in my later years of running the analytical lab, is that people wanted to go immediately to the best instrument we had. They'd always want to use the infrared spectrometer or Raman, or go to electron microscopy. And I'd first say to them, what did it look like visually? What did it look like at 10x? And they didn't know. And the problem with that is every level of magnification tells you something different about the unknown, about the specimen. And so the stepwise process really helps us quite a bit. So the eye, magnifying the image for the eye by stereo microscopy and then by polarized light microscopy is really an advantage. And I've got that described here in series as well. SEM-EDX, that's an acronym meaning scanning electron microscopy, energy dispersive X-ray, a whole nother presentation. And spectroscopy has to do with infrared or Raman, and it's the molecular interactions from beaming something and the interplay between molecules. Now, hopefully you'll be able to see what's on the right-hand side. I'm going to move this over for me. There we go. Here's a diagram of a simple polarized light microscope where we're still using a mirror, but we've got an incident light beam of white light, and it's reflecting off the mirror, going through a polarizer. Specimen would be on the stage here, passing through the objective. There's an accessory slot in case we want to modify that illumination. There's an analyzer, and a Bertrand lens just means a lens that's inserted, allowing us to see what's called the back focal plane of the objective. And it gives you an indication of what crystal system you're looking at. I'll explain that in a bit. And then the ocular is the eyepiece that magnifies this objective image. Notice that the diagram shows a 360 alignment of vibration perpendicular to this incident light beam, and that's the nature of white light. But as it goes through the polarizer, now it's aligned along a certain plane, and it passes through the specimen, through the objective, and all of a sudden we have an analyzer, which frankly is the same thing as a polarizer. It's just turned 90 degrees. And lo and behold, as light comes through here that's coherent and aligned, if something doesn't happen to it here at the specimen, it's not getting through this analyzer. And so that's the whole nature of polarized light microscopy, using that simple position of polarizer, specimen, analyzer. And so here's a diagram of polarization. And as I showed before, this schematic's a little bit different, but unpolarized light is vibrating 360 degrees around that propagation line. And it passes through a polarizer, and now it's all aligned. The only thing that gets through is this vibration direction. So right away, we've lost some light intensity. And at this point, we can use it to analyze our specimen. We can also throw in an accessory called a quarter wave plate. There's others. And now we can give ourselves circularly polarized light, which, you know, starts to bend your brain a little bit with how that can happen. But it's an effect that's been in use for a century or so. And we've used it to our great advantage. It's very simple, but it's very powerful.
I have a question, Scott.
Yes.
We put polarizers on our camera lenses at times.
Yeah.
So would that be considered a linear polarizer?
Yes. And it's basically getting rid of the stray light and augmenting the throughput light that comes through that polarizer.
Okay. Okay, thanks.
Sure. And you can also get polarization by reflection. The diagram in the upper right that incident unpolarized light strikes a flat surface, and now it comes off of that surface aligned in a certain direction. Not perfectly, but it's predominantly aligned in a certain direction. And that's almost exactly the example of out on a fishing boat and looking at the surface of the water and the sunlight glinting off that surface keeps you from seeing anything that's within inches of the surface. Put on your polarized sunglasses and you can see it. So that would mean that your polarized sunglasses have a north-south orientation, only letting in north-south light. If this reflection polarization came off east-west, now our north-south blocks it, and that's how that works. So for me, the nature of material is pretty important. It's everything that I use in trying to identify things, and frankly, what I would use to generate some cool photomicrographs. And I can describe it in a number of ways, but I'm just talking about solid materials now. We can have material that's either amorphous or crystalline. And frankly, more things are crystalline than you would think. Even our hair is crystalline, our skin. A lot of biological materials are crystalline. You usually think of crystalline materials as simply minerals, but there's a lot of things that have a double refraction. So amorphous materials means that they're not ordered. There's no sort of brick wall arrangement to their symmetry. They have a complete lack of symmetry. So window glass is a good example. If I were to take a ton of bricks and drop them off the dump truck, it's a ton of bricks in a pile. And although each subunit of the pile is a brick, and let's say chemically equal, they're not crystalline because they're completely non-symmetrical, non-aligned. If I were to stack up a wall of the bricks, just a wall, then I might have a two-dimensional order, and that might be thought of as a liquid crystal, because liquid crystals tend to have a two-domain order, but lack a third dimension order. You kind of have to think of those bricks as having very thin depth. And then with crystalline materials, they can have one refractive index or two or three. And I know that's confusing because I just said amorphous material has one, but there is an example of the perfect crystalline material, and that's salt. And in the upper right, you see a squarish sort of blue-white grain in the center, and it looks quite square. In fact, it's an octahedron because it's got a point in the center with 1, 2, 3, 4 faces on both sides. And that's an example of a crystalline yet isotropic material. Whereas if I were to dissolve the salt and let it dry on a plate and it didn't recrystallize, it would be an example of an amorphous material. It, however, would have the same refractive index as the crystalline material. So we can use that to identify it. So crystalline material is isotropic or anisotropic, a term that means it's got 2 or 3 refractive indices. And it can exist in a number of states. It can be perfect. It can be perfectly formed with no defects, perfectly ordered. It would give us a wonderful X-ray diffraction pattern. Everything's great about it, chemically, physically. But then it can also exist in a crystal continuum. In other words, it might have started out perfect, but now has what would be called phase boundary transitions, or it just has changed a bit over time, or maybe it didn't crystallize exactly in order. I built a brick wall, and in fact, I built a brick cube, but now the second and the 76th and the 150th cube or brick is missing. So it is the material that I suspect it to be, but it's just not quite right. It can also be imperfect with ingrains. it can be spatially organized. In other words, everything's at the center or everything's at the outside. And it can also have inclusions. And the photo next to that shows rutilated quartz, where the quartz solids in the northwest part and the southeast part, they just look like sort of fuzzy solids, but they don't have anything on the inside. Whereas this guy in the center is a relatively transparent solid, but it has goldish solid material within it, and those are bands of rutile that were in grain growth within the quartz rock. And of course, that's favored in some gem circles. It's a defect, but it's favored. And so a gemologist might look very carefully at the stones that they have to look for imperfections, to grade them. It's also a good way to identify them because they're not going to change. Some stones have air inclusions and liquid inclusions. Excuse me. So here, this slide shows the different crystal systems, and I don't want to drive you bonkers here after dinner, but on the right we show the isotropic and the anisotropic varieties. Isotropic is the cubic or isometric system, and all the other crystal systems are shown on this right-hand side, and they're shown diagrammatically here. So if I had a perfect crystal of each one of these systems, they could be stylized in a unit cell this way. A unit cell just describes, if you break it down to its base state, just what sort of angles the axes would take, what the relative length of each axis would be, and the angles between those axes. And you can determine all this microscopically. So you can take a single grain and determine its crystal system and possibly its identity. Not easy, but it can be done. So the effect here is the archetypical white beam through the prism and breaking it up into a component wavelength. Icelandic spar or calcite is a very famous and historically relevant crystalline material, very common. And I do believe the Vikings used this to navigate across the ocean. But you can see with light passing into and out of, by reflection, this piece of calcite, you can see that you get a double refraction, and that's because the material, the light passes through this material in two different rays called the ordinary ray and extraordinary ray. It's most pronounced with material like this. Usually with most minerals and other transparent materials, it doesn't break the light up this coherently and distinctly, so it's not easily done by eye. You have to use an instrument. So what about forensic microscopy that I used and generates great photomicrographs? The background of this title slide is a piece or a very small section of niacinamide, a vitamin, and it's a relatively pure material. It's probably a 99% source material, but you can see from the northwest to the southwest, really a wonderful display of color, and that color has everything to do with the chemistry of the specimen, the orientation, the thickness, and that all becomes diagnostic in time. But it's a pretty cool photo. So really the workhorse for any kind of forensic investigation becomes a stereo microscope. And I can see where you may use one in some practices. I mean, for pond water, for flower examination, for other materials that you'd like to observe from 1 to 10x, it might be a really helpful device. And you see a external incident illuminator revealing material on a microscope slide. And you can tell there's quite a lot of room between the objective and the stage. With a compound light microscope, we wouldn't have that much room. It's called a stereo microscope because the optical axis is about 5 degrees off. And that gives us almost a stereopticon sort of view. It gives us a much better depth of field. And so it helps us put these samples in perspective when we're first examining them and trying to manipulate them for other tests. And so our first evaluation is sort of obvious, physical features. And then we can go on to do other more simple tests to try to range find and figure out what the material might be. It allows us to take a fair amount of photographs, and we use it to prepare the material for the next test. I have one here at home. So how do we analyze materials? Well, we look at everything. We look at it first, we look often, and we understand what we see. I was trained in part by Walter McCrone. He was the microscopist that was sort of the outlier in the Shroud of Turin. I don't know if you've come across that before, but that's his claim to fame, or what he's infamous for. And the distinction here is that we're not really using this discipline for trace analysis. We're using it for micro and ultra micro analysis. So in other words, a homogeneous trace concentration of something, let's say looking for PCBs in groundwater or PFAS or something like that, the analyte or the material you're seeking is assumed to be homogeneous within the unit of the sample that you have in front of you. And so you can quantify the material according to the unit volume that you're examining. For particle microscopy or looking at foreign material, we're really looking for that little black speck in the cube. And we could have a high concentration of a singular material just in one spot of the cube. So it might be, on a concentration basis, it might be part per million, but on a visual basis, we might see black specks all over something. And so that's how it becomes objectionable. So for crystal diagnosis, we're using all of these features: morphology, refractive index, birefringence, which is a measure of the difference in refractive indices. Remember, I said if it's a crystalline material, it'll have 2 or 3. And so birefringence is the maximum difference between low and high. We use a property called extinction and another one called elongation, looking at the orientation of the refractive index. And another feature called pleochroism, which is separate absorbance of light along crystal axis, which plays out to, if I turn it to 0 degrees, it's red, and if I go over to 90, it's mauve. And that can be a diagnostic feature for certain gems and other crystals. This chart that looks like a rainbow, it looks like gas on a mud puddle, frankly. It looks like interference fringes, and that's pretty much what it is. It's showing you the what's called retardation of the light rays from each other as they pass through material. And the greater the difference in refractive index, the thicker the material, the more pronounced these colors will be. And I can use those to my advantage in preparing slides for optical art. The 2 images at the bottom left, frankly, are images of thick sand fragments of quartz. And the left one is simply white light. It is polarized light, but it's just plain polarized light. There's no analyzer. And the one on the right, once we stick in the analyzer, we block all the light. Since there's nothing to turn the light through the crystal, but once the polarized light goes through the crystal and it goes down 2 different hallways, basically, and comes out the other side, we start to see the color fringes, which all have to do with thickness. So if you look at the perimeter here, see how it's grayish into red right there? And then you can count the color fringes as you go up in thickness. So at this thick point, we're 1, 2, 3, 4 color fringes in. And so we're up into the 3rd and 4th order on this chart. And it's a way to visually, quickly say, oh, gee, I think I've got grains of XYZ in this sample because I know at a certain thickness, there'll be a certain color. Sort of reverse engineering for crystallography. And the nature of material, there's a lot of varieties we would want to describe. Do we have a single crystal, or is it just an air bubble? Is it liquid? Is it combinations of different states? Are they aggregated together? Are they fused together? Are there layers? All sorts of features you can look at microscopically to identify an item or assess what it's been through and to determine whether or not it's sufficient to use as a raw material or if it's been abused. There's also something called Thermo Microscopy, and these are melting grains in silicone oil. It's a photograph taken while they were melting. That's why they all look rather rounded. But you can take several grains in this prep and conduct a melting point operation. And you can tell whether or not it was a hydrate, or a solvate, if it releases gas. You can look at the relative crystallinity in these grains. You can see those fringes again. And you can perform experiments to prepare different thermodynamically stable forms, which might be something you can use to patent a new form of a drug, which we've done. And I remember I talked about crystal continuum, which usually ends up as a suboptimal physical condition. And in this upper photomicrograph, it's from Polarized Light microscopy. These are 10 micrometer size domains. You see that some parts of that solid are rather light, and then other parts aren't light at all. And so what's happened here is this drug, through heat and pressure, has changed state somewhat, and some parts of it are more amorphous and other parts of it are crystalline. And that may affect its solubility, its stability, the way it processes. And it's just another feature to look for. So you see, when the pharmaceutical companies complain about charging a lot for drugs, some of it is to pay for investigations like this. Maybe not much of it, but some of it. Here's another example of, or really 2 examples of, let's say, striations in a material that's been machined so that the particles are very small, but now this mass of particles, they've clumped together, and they've clumped together in various zones and created a rather suboptimal outcome. And so we would want to try to avoid this in the machining or micronizing of a drug. And in this image in the bottom right, we're looking at aggregates within an array of a normal drug, and we find that even though the quantity is really low, that's objectionable too. It'll affect the processing. So, is it art or is it analysis? Yes, it's both. So if I look at macro photography of the common biologicals, for somebody like me who's looking for contamination, we have to be able to recognize this on site and analyze it and figure out what it is, where it came from. And you can play around with these things too and make them look pretty cool. As Shirley alluded to, sometimes she loved me, sometimes she hated me. Usually what I would get at project team meetings when I would show folks the results of an analysis, they'd say, oh, well, that's all well and good, Scott, but man, those are pretty cool pictures. How'd you do that? And that early on got me thinking about generating photomicrographs of fusion preps. But remember I said earlier that even your hair is crystalline, and you can see in this human hair, this is the center is air, but you can see the birefringence in the outer shaft of that hair. So you can examine hair for damage and cuticle thickness and hair thickness, on and on. A couple of examples of synthetic fibers. They look a lot different than hairs. Of course, they won't have any scales. That's the big difference. But again, thinking about that that rainbow map of the Michelle Levy series, see all these color fringes that are here in the polyester, and not so much in the rayon. So immediately, I'm looking at a high birefringence non-scaly fiber, and I think polyester. And rayon is an extruded cellulose, and so it doesn't have that same sort of feature. Here's two examples of cardboard. One cardboard and one Tyvek. Cardboard would be pretty objectionable in any pharmaceutical, mainly because it shows a lack of control, aseptic control, and it's a vector for biological contamination. On the other hand, Tyvek, we might see that a lot too, because people's isolation suits are constructed from Tyvek, and so having Tyvek in your sample as well is not a good thing. And so in this slide, I'm just showing a number of materials here that are almost instantaneously recognizable to the practitioner. Again, you all can tell that's polyester. I just showed it to you, and here's some cardboard. But this is a segment of a closure, a rubber septum, the sealer that goes on top of a pharmaceutical vial. And you can see that it's not completely homogeneous. There's little speckles in it from the carbon black they use to color it. In the upper right, this is some solids from a spice mixture. There's some salt grains and pepper and other items from the herb mix. The image with the blue background is an example of beach sand, and freshwater sand at that, because it doesn't show the sort of foraminifera and other sort of organism shells that ocean water would have, diatoms, things like that. Bottom right, fiberglass, characteristic, very fine strands of glass with the glue that holds them together. Both characteristic of who made the fiberglass and when, if you're tracking that back. The image bottom center is an example of a variety of minerals in a microscope prep. And there's quartz and calcite and hornblende and apatite, a variety of minerals in that mix. And in the bottom left is a cross-polarized shot of glass plus, quartz plus glass. So quartz is the one that looks like a little Hawaiian island here. And remember I talked about that fringe, you could tell the thickness. So in the very center, it's the thickest, and it goes to a very thin edge. Same thing here, same thing here. These three are all quartz. And you can just see 2 or 3 objects that don't have any color at all. And chemically, it's the same. It's SiO2, silica. But it has no order, and it's amorphous. It has 1 refractive index, and so there's no opportunity to get 2 competing light paths through the solid that set up these cool colors. So, art. This is called a fusion prep. And a fusion prep is simply taking a meltable material and melting it quickly between a cover slip and a glass slide, and then letting it freeze and examining it for its effects. Now, from an artful standpoint, you just keep doing this and playing around with it until you get the images that you prefer. From an analytical standpoint, you might be looking for things that would grow in this boundary between, in this example, the Northwest and the Southeast, and then you know, what are these long spears all about? And if this were to be carefully analyzed, you might find that these are different polymorphs of the same chemical compound. But for me, it's just, this image is just pretty cool looking. Now this image, I was taking some images one day, and we ended up calling this Froggies Pond. I had a series of images that I generated. I thought they looked pretty good, but I hadn't named them yet. And my wife came home from work and looked at what I generated and said, "Oh, that looks like a frog." Not this one, and that looks like Froggies Pond. So that's what we named it. But again, this is all the same chemical, and this is a void. It's very thin here and striated. It had nucleated here, another void. But the way it aligned, it just made a striking image. Niacinamide again, these long spears that were an intergrowth into these other displays. These are all based on thin and transparent solids. I'd say the domain measurement we're talking about here is about 500 micrometers across. A human hair is about 90 micrometers across. And so we're looking at very small domains in a solid and transparent material. So sometimes the images that you see remind you of things. And this painting by Rousseau, to me, evokes a jungle scene and a lush landscape. So when I saw this image for niacinamide, all I could think of at first was banana leaves and the lush tropical rainforest. And I ended up calling it Gaia flag, probably because I had too much bourbon that day, but it's always been one of my favorite images. Here's an original image of propylparaben. You see the field is largely black. That's because there's nothing there. It's just an air void. And then the magenta, ochre, orange spicules, I'll call them. That's just a crystallized propylparaben, which is a common preservative. And the image on the right, hey, I gotta play around with the colors sometimes. So they're really the same images, but the colors have been modified a bit. Here's an example of a different preservative, photos taken while it was melting, which I always thought was pretty cool to see the grain boundaries in the crystals as well. So in this lower southwest section, it's an air void, but this is all the melting liquid around it. And the solids give a structure and color mainly based on their thickness and orientation. Rotating this 90 degrees would show you pretty much the complementary colors. And the image on the right, same thing, different part of the field, and pretty exotic colors and structure. So a lot of fun. I think I'll end it there. And this last image is really the worst thing that you can end up with for a pharmaceutical solid. If we wanted to take a antibiotic and process it as a powder for either filling into vials or using in manufacturing, we would want it to all be like little salt grains. And when it forms what are called spherulites like this and these long needles, it's hell to pay to try to dissolve this very quickly. So I took this image of what to a pharmaceutical chemist would be an unwanted solid, but to me it's very pretty. And it's got an interference plate that just changes in thickness as it passes through the field, and so that's why we have different colors. So I'll stop my share there. Oh, good, you're all awake. That's great.